Howdy guys. In this video we're going to take a look at using VOPs, also known as vector operators in Houdini. So first I'm going to go in a little bit and explain what VOPs are in Houdini. VOPs are used for everything from building shaders to modifying geometry and much more. They kind of act as wrappers or visual node-based representations of the VEX code. So like a visual representation of the wrangle nodes. So to demonstrate kind of what that is, I'm going to do a quick example using a line and some points. And we'll go ahead and add 2 points. And just that. Alright. And we'll group these. Okay. So now let's go and resample our line a little bit. Let's do something like 15 points. And then once we have our line, we'll go and make a point VOP. And you'll notice when we add this point VOP, it doesn't change, nothing happens. So there's no user interface that we can type into in here. This acts similar to a subnet or a higher level node. We actually need to double click and go down inside this node. And we'll notice that these nodes look very different from the nodes that we're used to working with. One of the primary differences is that we're no longer working from the top to the bottom like our normal workflow in Houdini. Instead we're working from the left to the right. So similar to the wrangle nodes, the VOP behaves much like a programming language. It's a visual representation of the VEX programming language. So here, if we look in here, our input node is all of our parameters and attributes that we're used to seeing on our other nodes. So position, velocity, force, age, life, these are used primarily for things like particles, but we'll look down here and we'll see point number, prim number, vertex number, number of points, like we're used to modifying with geometry. So VOPs are primarily used for low-level operators, such as math operations, and oftentimes in geometry used for modifying point position, as well as color, normals, and UV space. We're going to take a look at how that actually can be used to affect our resampled curve over here. So, real quick, we can go and add this point position over to position. And again, nothing will happen. We're saying the global position attribute for our points is equal to the global position attribute of our points. But let's say I take the point number attribute and set that to the point position. And now, if I take a look at our front view, we'll see that point 1 is located at 1, 1, 2 at 2, 2, 3 at 3, 3, and all the way on up to 15. And if we actually look in perspective, it's doing this on all 3 axes. So we can see down here in our geometry spreadsheet that we're setting each point value to the value of its point number. And that's pretty cool. So what can we do with this? For this example, let's say we're trying to make something like a rope or a cable or something. Say we're going to support a bridge, like a rope bridge. So we want to have our initial points, so 0 and 15, our initial point and our last point kind of locked in place at their 2 starting positions, and we want the middle to sag. And we could do this with a soft transform or something like that, but those can get kind of heavy, and VOP are actually very efficient ways to do complex operations like that. So let's go ahead and dive in and see what we can do to start getting some kind of sagging effect on our points. we're going to first look at using our point number and the number of points. So we're going to convert our point number to a float. So we're just going to drag out tab and then to float, and we're going to make an integer to float. And here we'll, at our num points, we can drag out. We want to get the use point numbers. The number of points is always going to be the number of points we have plus 1, because it starts our count at 0, and we need to go 0 to 15, so we'll subtract 1. So we'll just do num points subtract by a constant, because we just need to subtract 1. And once we've subtracted 1, we'll go ahead and convert this to a float as well. And then we're going to go and divide the point number by the total number of points. And then when we so we need the operations we're performing here to affect our global point position. And we want this to affect the y-axis. So we'll go ahead and break this point position out from its vectors. So we'll say to float, and we're going to grab a vector to float. And this will break our vector for x, y, and z into 3 values. We're going to go ahead, and we only want the y value, so float value 2. And we're going to break this back into a vector, so we'll just say float to vector. And we're going to connect this over to our point. And now we'll see all of our points, because we only have x connected, have all collapsed to 0 on the x-axis. We'll move this back over to 3, and now they're spread across on the z-axis. So we will need to move these guys over here farther to the right, and on here we'll just drag an add node, and then move this add up into our y. And then if we connect these values, we'll see that now our y is being offset by the point number divided by the number of points that we have. But this isn't really what we need. We're actually going to need to square this value so that we can take our slope and turn it into a parabola. So we'll drop down a multiply, and to square it, we'll just multiply it by itself. And now we're starting to get a little bit of a curve. Actually, let's increase the steepness of this curve, so we'll multiply it by a constant, and multiply this by 2, and we'll subtract 1 so that we can drop this down a little bit. And now we'll square this again, and there we go. We have our curve starting to sag. But it's a little too high, so we're going to need to take the complement to invert this and then negate it to drop it back down and get our beginning and end points where they belong. So we're just going to drag these guys a little farther out, and we'll come out here and make a complement. That'll flip it, and we've got our 0 and $n points, our first and last points, in their correct positions in line with the origin axis. And then we'll just negate this to invert it back to our sag. And that's how we can use VOPs to add a simple sag to our point line. And really, we can do something a step further and start adding and creating our own parameters that we can then expose and control to control the amount of sag that we have. So to do that, I'm just going to hit tab and start typing parameter, and I'll make a new parameter, and we're going to call this parameter the hang amount. And I'm just going to give it a label, call it hang amount, And we could set the default value and range, or we could not. It doesn't really matter. These are the values that will appear on the sliders, but they have no actual physical locked range themselves. So let's go ahead and multiply this hang amount by our negated, and we'll bring this into our input, and we'll see that we now have a flat line again. But if we go to our parameter and change our input, we'll see that by moving this curve, we're actually increasing or decreasing the amount of sag evenly in our curve. And what's more, if we step back up, we'll see that we now have an hang amount attribute exposed here in our attribute VOP. And we can middle mouse and increase the amount of sag that we have here in our VOP. We could even invert this to get a nice hump. And remember, this is really just a visualization of the VEX programming language. So all of these operations that we've done here, we could easily have done in an attribute wrangle using VEX normally. So we can actually right-click this node and go to our VEX and VOP options and just view the VEX code that made up this operation here to see what it does underneath this, the hood. And this code at first looks a little bit overwhelming, but it's actually very efficient, and creating things using VOPs is negligibly the same as it would be to just type it directly in a VEX expression. So what we have here is a pretty good way to make the start of, say, a sagging rope bridge or something like that, or maybe some wires. And now we're going to take a look at how we could start using a get some variation if we wanted to have a lot of wires hanging from something, or a different way to use some more parameters in our attribute VOP. So we're going to take these guys and drag them over here to the right. We're going to make another resample node. And in this resample, we're going to do max segments. Let's do something like 20. And we're going to increase our distance here to something like 30, just to get some more length here. And we'll actually just do like 5. That'll work. Okay, so what do we want is we want this sag to happen for every single segment in our curve, in our line. And so we could do this using a couple of methods, one of them being a copy stamp and perform a unique operation based off of a stamp attribute for each point, and that operation could very well be something driven on our point VOP by linking the hang amount. Another way to do this is by using a for loop network inside of Houdini. So let's take a look at doing that. So we're going to need to do something real quick to set up our line to be ready to be used inside of a for loop. So we're going to actually use a carve node so that we can access or break apart our single line, which is right now a single primitive, into a separate polygon for each segment in our line. So we're going to turn on our first and second U in our carve, and we're going to start at 0 and go to 1, so we have the full length of our line. And then we're going to go to breakpoints and then cut at all interval U breakpoints. And now if I turn on point numbers, we'll see that I have 0, 1, and then 2 to 3, and 4 to 5, and 6 to 7, and 8 to 9. So it has cut all of our segments into its unique primitive. And I can see this by middle mouse clicking and looking. Now I have 5 primitives in our line of 10 points. So now that I have each of our segments broken up into separate primitives, we can go and type a for each, and we'll get a for each loop. And this is going to create 2 nodes and this nice outline here. And so we can move this block around and move the bottom node down, and this is a visualizer to say what will happen inside of this network here is going to happen for each of the elements that we write in our end block. So notice there aren't many options in our begin block, but in our end block we can define attributes. So if we wanted to iterate only primitives coming in that had a specific attribute, or navigate around that attribute in particular, or just all of the primitives piece by piece. And we could operate over points as well if we wanted. So we're going to start at our begin block with our first primitive segment. And we're going to need to resample this segment so that we can start adding a sag for this segment, just like we did for our previous segment. So 10 segments, let's bump this up to 15 or so, and then we can actually just copy this point VOP that we made earlier and paste it into our for each. And we'll see we get this sag. We have our sag amount right here. And then if we go down to our for each, we'll see that now each segment is similarly sagged. But what if we needed to add a random sag amount per segment, because we don't want them to all be completely uniform? That'd be pretty easily done by going in and modifying our point VOP a little bit. So what we can do here is after our sag amount, or before, it doesn't really matter, we'll just drag this out and we'll make a new parameter again. And we're going to call this rand hang, random hang for our label. And we'll multiply that value again and add that in. And by default it's going to be 0. And here we can write a random function and have it choose a random hang amount based off of the segment that we are currently in, or the iteration that we are on in our for each block. So in order to see for each, which is an attribute inherent to the for each block, we'll actually need to go to the beginning of our block and create the meta node. And what this will do, if we go over to our detail attributes, we'll see that we have two new detail attributes, number of iterations and the current iteration that it is operating on. Now that we have this iteration detail, we can reference this attribute in our point VOP expression. We can actually start typing a rand expression here, so we'll do rand. And then we're going to need to grab the detail attribute off of our block begin for each metadata node. So we'll do a detail for each begin 1 metadata 1. And we're going to be grabbing the iteration attribute, and we'll say the default value is 0, and then we'll do a second parentheses to end our rand function, and we'll hit enter. And now when we go down to our for each, we'll see that we're getting a slightly random sag amount for each of our nodes. And this will become more apparent as I increase the sag amount on our cables. And if we wanted, we could multiply our iteration by another number and then modify that number to change our seed. Notice that in doing this method with simply multiplying, our first iteration is always going to be the same, because almost every seed by default is either going to be 0 or 1. So we're going to alternate between those two seeded operations. We can change that by just adding a plus here, and then we'll get more randomness across each of the segments in our rand function. So now that we've got our point VOP happening inside of our for each loop here, let's take a look at how we can add some points and extend them off of the end of our curve using the polyframe point VOPs and some point attribute expressions. So we'll just drag this off of here, and first thing we're going to need to do is create a join node, and I'll take a look here. We'll see that again we have 5 polygons, where we want this to be one continuous polygon curve. So our join node will actually combine all of those polygons and clean up our overlapping points and vertices that we would have here. We'll turn on point numbers and see that our points no longer double up. So first thing we're going to need to do is isolate our beginning and end points so that we can start creating the trailing lines for our cable or wire. So to do that, we're just going to make a delete node, and we're going to delete by the pattern 0 and $n to delete, let's do points, not primitives. And right now this will delete the beginning and end points, and we'll just change this to non-selected so that we're left with our initial straight line again. And then we're going to need to take a look at the point normals here, which it by inherently, if we take a look at our point attributes, doesn't have normal attributes. So we'll need to add some. And we could do this in 2 ways, and I'm going to go over one way and why I don't recommend using it, and then another way that I prefer because it works better in more cases, such as this. So first, we'll take a look at the attribute expression. And one way that we could do this pretty easily is adding a new normal attribute to our points, and then setting this to value. And we want one point to look that way, and one point to look that way. So if we were to set this, say, to look at Z, and I'm going to go and turn on my scale normal visualizers to make this a little bit easier to see. Okay, so now our normals are pointing here towards the right. But what will happen is we actually want them to point tangentially from the direction that they're pointing, the direction that the line is angled at. So if we actually go to our add node, and I'll hit enter in this viewport to start moving it, we'll see that as I move it, our normal no longer points out from the direction of our line. It's pointing always in the right positive Z direction. And this isn't really what we want. We want it to point diagonally out to our line so that when we create a new point on our new line and align it to the rest our previous line that we've drawn. Instead of our point VOP, our point attribute expression, is use the polyframe node. And what we can do here on our polyframe is set our tangent, our normal, equal to our tangent. So we're going to have this work over points. I'm going to turn off our normal name and change our tangent to our normal attribute. And we'll see here that our attribute is pointing now here towards the negative Z-axis, but as we go back up and move our line, we'll see that it is always going to be tangential or in line with the angle of our curve. And this is the behavior that we want. But here we'll see one of them is pointing in the wrong direction. We need it to point in the positive Z direction. So we're going to need to reverse that normal direction, which we can do quite easily in a attribute VOP. So we'll drop down a delete node so that we can isolate the point we want to work on. And here we're going to want to go over points, and we'll just delete 0 so that we can have just this point isolated. And we'll make another point VOP. And this is going to be pretty easy. We really just need to grab the normal attribute here and negate it or invert it, multiply by -1. and flip that normal to the other direction. So we'll just type negate, bring it into our normal, and we'll see that now the normal is facing the opposite direction. Pretty simple. And now we'll go through our polyframe, and actually we can just copy this delete node, and we'll just delete non-selected so that we have our other point, and we'll merge these two back together. And now we have our 2 points with normals facing in the correct directions. So now we'll make a new line. We'll have it orient to the z-axis, and we'll copy 2 points so that we now have an end line originating from our endpoints of our original sagging lines. So really now, just select these guys and pull down from our join, and we will merge these together over here. Notice we get this warning here. If we double click it, we'll say we have mismatched normal attributes. So we can either do 2 things. We can update the normals over here and create normals for these nodes, or we can remove the normal attribute from this side. So in this case, I'm just going to do an attribute delete, and we're just going to delete the normal attribute on those points. And now our warning is gone. So do a couple more things to clean up this curve. So first, again, we're going to need to join these nodes, because now we have this primitive, the primitive that we previously joined here, and this other trailing primitive here. So our join node will clean that up. And now we're back to just one polygon primitive. And then if we take a look at our point order, it's all kinds of screwy. Always see 0 is here, but 77 is all the way over here at the end. And we're going to want to clean that point order up, because it may cause issues if we're trying to reference points in a specific order or perform points operations by point number in the future. So we're going to make a sort node, and we're just going to sort our points by vertex order. And I want it to go from left to right, and so we'll just reverse that point sort. And now we have 0 to 1 all the way over to 77 here on the end. And if we turn this off, we'll see that our line is pretty straight. There's not really an interpolation between where we start sagging and where we stop. It's really sharp. So we can actually convert this to a NURBS curve from a primitive curve to add some more interpolation between those points. And we'll go ahead and decrease this curve order, U order a little bit to offset some of that height that we lose from this softening of the edges. And we'll just convert it back then to a polygon curve, and we'll see that now we have a lot of points, but our curve is once again smoothed. And we don't really need this many points. We really only need the points where we have more things changing. So we can clean up our line even more with a refine node, and we'll just again have this iterate from the beginning to the end of the node. And we'll go to unrefine, and that actually looks pretty good right there. But we could increase the tolerance to have less points, or increase it to increase the smoothness and the interpolation between the points. And I actually think I liked it how it started right there. That was pretty good. Once we have this smooth interpolation of points on our curve, we can create the outline for our wire, and we'll just go make a sweep, bring this in here, and we'll decrease the scale of our wire. And then once we have our sweep, we'll just output and skin this with preserve shape. Oh, it disappeared. Oh, it is because I'm using a primitive and I should be using a polygon. There we go. And there we go. We've got some nice hanging wires. And we'll see that if we go up to our point VOP here, we can modify the sag amount. That's pretty nice. And again, we can still change the random seed of each sag. And once again, with the beauty of Houdini, we still have our original points here for where each cable or segment meet to have our sag. So as we have the sag points here, we could actually use the resample from up here, move this down here so we have easy reference to it. And we're actually going to need to delete the beginning and ending points. So we'll do 0 and $n again over points. And now we have just the center where we would want to apply our hooks. So for this, I'm not going to spend too much time making these look like the most beautiful hooks in the world. Really, for demonstration purposes, I'll just drop down a torus, and we'll just say this goes in the z-axis, and we'll do a v-wrap, and and we'll just have this go to 180 here. We'll give it some end caps. Decrease the rows. Maybe make this a little narrower. Okay, that looks fine. So now we can copy to points. And we've got, probably need to set a transform on this to move them up to our sag, but we'll see after we merge our hooks to our curves. And there we go. That's pretty good. That's kind of a quick introductory overview to how to use the point VOP operations, as well as how to think about using the for each block structure in Houdini.